Let's discuss the problem 4 of tutorial number 5. In this problem we have considered a rope of length L. So this rope is of length L and mass density lambda, which is equal to capital M by L. I am calling this capital M as the mass of this entire rope. Now suppose we fix the ends at points x0 and y0. Fix this x0, y0. This is one point, and x1, y1. So we have the coordinate system. So let this be the x-axis and this be the y-axis in Cartesian coordinates. Okay. Suppose we fix its ends at points x0, y0 and x1, y1 such that the rope is hung between two supports of equal height. Let this support be of at equal height. So some height h, which means this rope is at some height h, which means if it is under the gravity, there will be some potential energy on this rope. Okay. And this pillars are separated by a length p. This is also given. Now the question is, what shape does the rope make when it hangs under the influence of gravity? So there is gravity downwards acting. So to find out what shape it will take, you should understand why this every material takes some different shapes when it is left alone, or when it rolls down to a different position, or if it is a liquid, it flows down to a downward position. You should know this is because to minimize the potential energy. Okay, so this rope, since it is tied at two ends, will make this kind of parabolic kind of shapes. I already drew in that way, but that is because of our common life experience. It takes some shape like that. Why? That is because this position is the minimum, most possible minimum potential energy this rope can attain. So how will you find out that potential energy? To find out that potential energy, what I am doing is I am taking a length element ds here, such that I can find out the potential energy for that small length element ds. Then I can integrate it for the whole rope for entire length dl. That's the idea. So how will we do that? So let's look at the potential energy of this ds element. So what will be that potential energy? Du will be equal to dm y. Y will be this height. Okay, so I did not mention y will be the height from this ground. So dm y into g, that is gravity. So what is this dm? This dm is equal to lambda ds. Okay, it is coming from here. So now you have what is ds, that is under root of dx square plus dy square. I don't have to explain this, as I understand, because we have been discussing about this from the first tutorial, how to find out what is that length element. So substitute it back to du. You have this is equal to lambda m y g under root of dx square plus dy square. This is your potential energy for the length element. So what will be the total potential? Total potential will be du integral of du from where to where, from 0 to L, lambda m g y. Now while I am substituting, I am taking this dy square as common, so this will be dx square upon dy square. So let it be like this into dy. This is what we have. So let me rewrite this again. 0 to L integral lambda m g y under root of 1 plus x dash square into dy. This is what I have. I am defining this x dash as dx upon dy. Okay, so I am rewriting this again as 0 to L some f function of x comma x dash comma y into dy. Now compare this equation with the equation you have, that is action equal to L, that is q dot into t, function of L q dot into t dt, which you call as Lagrangian, and you obtained an equation called Euler-Lagrange equation, which is equal to d by dt of del L upon del q dot into del L upon del q, which is equal to 0, by minimizing this action. So we define that if we minimize this integral, what we get is the shortest path it will take, the minimum action it will take. Okay, so if we take the same concept here you see this function is this f is a function of x dash and y, where you see the similarity here. X is like q, x dash is like q dot, this y is like t. So if we apply, so the minimum potential, to get the minimum potential, what we have to do is just find out the Euler-Lagrange equation for this function. So what will be that Euler-Lagrange equation? That will be d by dy into del of f upon del x dot minus del of f upon del x equal to 0. Clearly from this equation you see this is what is f here. F is equal to lambda mg y into root of 1 plus x dash square under root. So this is your function. Clearly this is not a function of x. Function means there is no x dependency, explicit x dependence here. So you can see this, you have to find only this part. So now you can find it out and integrate it. You will find out a relation between y and x. So this relation will give you the shape that ROP will have, such that it will be at minimum potential. So this is the method. I'm counting on you to do this part of the problem. So thank you for watching the video, and let's see you in the next problem.